All right, welcome to our webinar today, a data science breakdown with SenseCorp. SenseCorp powers insight-driven organizations. We turn data into actionable insights and transform organizations for the digital era. We have been around for about 2 decades and have been rapidly growing in the data science space. As you can see here, we do everything from enterprise data strategy through advanced analytics and data science. Today, I have the pleasure of introducing a few of our very talented data scientists who are going to be your panelists. Levi Joseph, a data scientist with past experience in supply chain management and maintenance roles in the transportation and energy industries. He'll be discussing a population health approach to modeling maintenance outcomes in different industries. We also have Justin Nguyen, who's a data scientist who specializes in machine learning. He will be introducing a few useful ways you can apply data science to your business. And finally, we have Dan London, who's a senior data scientist who works primarily in SenseCorp's telecom segment. He'll be discussing the benefits and challenges of leveraging models developed in one industry to answer similar questions in another. I'm going to go ahead and pass it to Levi to kick us off today.
All right, guys. Thank you all for joining us again. Today I'm going to be starting off with a quick little data science 101, just key terms and concepts that are going to introduce some of the later things we'll talk about. So we're going to start with a poll. Should be popping up. So how familiar are you with data science? And panelists.
Yeah, you can go ahead and answer that now, and we'll share the results in just a minute. All right, just a few more seconds here if you can get your answers in.
Awesome. Thank you all for participating. So this is about what we had expected, and we've kind of calibrated our presentation material today to cover a wide swath of expertise levels. And if you all have any questions that come up, if I or one of the other panelists say a term, feel free to hold on to it at the end, and we can make sure we explain any things. So moving on. So this idea of data science is kind of a new term, and you'll find a lot of different definitions if you go scouring the web. I've gone ahead and pulled a few that I like. So the first comes from Investopedia, and it's data science combines different fields of work in statistics and computation to interpret data for the purpose of decision making. I think it's pretty concise and hits all the key concepts. Another one that I really like is a little more broad. Data science is the study of generalizable extraction of knowledge from data. And this, I think, really gets to the core of what we're after when we do data science, which is the idea of turning information into insight in a generalizable way. So a way that can actually go beyond the data set to improve your business or your organization. And then lastly, it's one I find funny. Data science is what data analysts say when asked what they do for a living at a bar. Another similar one you might see is a data scientist is a data analyst living in California. Then this comes from Twitter, and I think it's important to be a little lighthearted when it comes to these terms. So I'm going to offer you our SenseCorp definition of data science, which is really an amalgamation of a few different definitions. So data science exists at the intersection of mathematical statistics, computer science, and domain expertise. It is an interdisciplinary approach to drawing diagnostic, predictive, and/or prescriptive insights out of large, complex, and/or exotic data sources using formal, rigorous, and reproducible methods. So not quite as concise, but I think it hits a lot of the key stuff. And let's unpack this a little bit. So this first idea of the intersectionality of data science, or the interdisciplinary nature of it, was first created in 2010. It's referred to as the unicorn diagram, which is basically this idea of data science really is a combination of multiple domains into one skill set. So upper left quarter of or third of this diagram is domain expertise, and that's really about the context that's necessary for either the business or the data to really understand and gain access to its full value. So from a consulting perspective, a lot of what we're partnering with our clients is they have the domain expertise or some of it, we have some of it, and we're combining it into our projects. The math and statistical knowledge component is very crucial. This is probably the hardest thing to learn outside of school, though it's not impossible. And really what that is it's for pre-processing your data, for building and tuning your algorithms, and then for interpreting the results. So a lot of the beginning parts of that pre-processing and the end, the interpreting is what's really left and what's really crucial for getting it right. Modern software has made a lot of the tuning and training of algorithms a lot easier, though without the mathematical understanding to know what's going on underneath the hood, mistakes can still be made. And at a specific level, this is really an understanding of linear algebra. So things like calculations of matrices and understanding dimensionality, as well as some multivariate calculus, trying to understand global minimas and maximas, and then a little bit of, well, not a little bit, a significant amount of just generic statistical understanding. And then finally, computing skills. So that's both the ability to write scripted procedures in R, Python, as well as to operate more GUI-based statistical softwares. And then also some distributed computing skills are becoming more and more important as we move towards these more computationally difficult algorithms, such as deep learning. So you'll notice, last little thing on this, data science is at the center of this diagram and not necessarily data scientist. And that's because it's hard to find an individual who has all three of these things. It's a little bit easier to put together a team of individuals who, in their combination, have all three. So moving on to this idea of types of analytics. So usually you'll see descriptive, predictive, and prescriptive. We at SenseCorp think diagnostic analytics are a crucial component of data science. So if descriptive analytics is either what has happened or what is currently happening, and that's more in the realm of traditional BI and reporting, the latter three are getting into the realm of data science. So diagnostic is really trying to understand what happened, or sorry, why things happened. And that's you're using kind of more classical statistical techniques like hypothesis testing, ANOVA, et cetera. Predictive is really kind of like the meat and potatoes, what you read about in articles or online. And this is, everything from time series to heavy duty machine learning, classification type algorithms. A whole host of stuff exists here. And then lastly is my own personal favorite, prescriptive analytics, which is what should be done about it. So given these awesome insights that our diagnostic or predictive algorithms are giving us, our approaches, how should we best act upon that? And you can use some cool techniques such as optimization or simulation to try and make the best decision. Getting into types of data, so large, complex, and exotic. So large refers to big data. That's the 3 V's, volume, velocity, and variety, or how much, how fast, what kind. But one thing worth noting is you don't have to have big data to do data science. And big data is kind of a relative term. What's big today will likely be normal in 10 years. And we've had a lot of success with smaller data sites in driving insights from them. Complex data. So this is your standard structured data that might live in a relational database, as well as unstructured data like text data, and even like hybrid data, which might be a combination of both. And then it can also go back to the architecture. So is it a distributed architecture? Is it like living in a cluster? Is it streaming data coming off IoT devices? This is all complex to deal with. And then lastly, exotic data. So this is the kind of like the data type or the nature. So is it natural language? Is it video? Is it images? What's cool about data science, or one of the things that's cool, is that a lot of these data sources that were previously not necessarily easily accessible or able to derive value from them quickly, now with data science techniques you can. That's very cool. So last part of this definition, formal, rigorous, and reproducible. So formal, so this is trying to be analytical, trying to remove the intuition or gut from our decision making, and it's automated. So we're trying to remove points where things can break by removing the human from the equation and letting the computer do as much as possible. It's also rigorous. So this is the idea of using hypotheses and doing things like designing experiments so that we can really understand the effect of different behaviors And then also we try to test different alternative hypotheses to make sure that we're kind of honing in on the ideal. And we always just try to be provable with mathematics. That's kind of what this all comes down to, is trying to be a little bit more rigorous overall. And then finally, is it reproducible? So a lot of what we do is scripted. So versus like ad hoc Excel or visualization-based kind of decision making, we're running a script that's doing something in an order that can then be audited later on to make sure we're doing it correctly, and that we can do it again over time. So last part of this intro, quick little glossary of terms. You can think of these like note cards. I'm not going to go too in depth, but so data mining is a subfield of statistics, and all data mining really is it's looking for underlying patterns within data sets. It's been around for a very long time, and it's kind of the core of all this stuff. Artificial intelligence, jumping to a pretty big term here, it's pretty difficult to define. You'll find a million different definitions. We're going to use this idea of any autonomous decision-making system, and it's very useful to think of artificial intelligence on a spectrum. So on one end, you have things like weak AI, which is an artificial intelligence that has a narrow ability to make decisions, so it can only make one or a few decisions, though it can do it at a human or a superhuman level. So think of this as like image classification. Humans might be able to look at a photo and tell you if a dog's in it. An AI might be able to do something at a similar level of accuracy, though it can go through way more photos way more quickly. Strong AIs is the other end of the spectrum, and this is kind of the scary, Terminator type AIs, or potentially scary. I guess they don't have to be. And these are basically artificial intelligences that have the ability to make a broad range of decisions at either a human or a superhuman level. And this is where you start to get into replacing humans with automated processes in a very broad way. So this just to kind of orient you. Machine learning is a subfield of artificial intelligence. So this is basically using those data mining techniques in combination with concepts in computer science like recursion, et cetera, to basically make better predictions over time about future outcomes. And this is kind of where most of the buzz is these kind of techniques, most of which fit on kind of the weak AI part of that spectrum. And this can really be broken down into three types of learning. So the first is supervised learning, and that's learning towards a specific or preordained objective. So I want to predict, is this car, is it going to be red, blue, or yellow? So I'm trying to basically predict something happening that's very specific. Unsupervised learning is learning towards no specific objective. And this is basically, you're giving an algorithm just basically a set of data, and you're asking it essentially to tell the user what's interesting about this data. What are the key clusters, the key features that are worth noting? And lastly, this idea of reinforcement learning, which is getting towards the current cutting edge. And this is learning towards maximizing a specific goal and giving it a reward for correct behavior. So it's really a mix of supervised and unsupervised. So a good example of this is the AlphaGo algorithm, which is basically a game playing algorithm. And it's supervised in the sense that it's trying to win this game, and we have to be able to identify a win versus a loss. But it's unsupervised in the sense the algorithm is given free rein to determine what strategies or what paths it wants to take towards winning. And you see a lot of superhuman type behavior with reinforcement learning, because basically these algorithms can in the game playing context, for example, it'll take strategies that a human either would have never thought of or would have taken thousands of years to think of. So pretty cool stuff there. So taking it down a level of granularity, so classification is a statistical approach that's trying to basically put things into buckets. So trying to, like I said earlier, that red, yellow, or blue car example, or another example would be if you're trying to predict if a baseball player will be like a Hall of Famer, an average player, or he won't make the majors, you might use a classification technique there. This is supervised learning, and it produces a discrete variable. So, something hard and fast. Regression is similar in that it's another supervised technique. And this is rather than trying to predict, a discrete outcome, it's trying to predict a continuous or frequently numerical outcome. So let's say I'm trying to predict how many home runs a player might hit in their career. That might be a regression type approach. And this goes from everything from your basic linear regressions into very, very complex tree-based or forest-based methods. Then lastly, this idea of kind of comparing and contrasting. So classification is trying to basically group data into similar groups, and this can go into multiple dimensions and multiple groups. Regression is more trying to fit a line or a hyperplane to a set of data. And then clustering is a type of unsupervised learning, and that's trying to basically take data and group it in a way where you're not necessarily like specifying the outcomes. You're basically saying like, just tell me similar groups. Maybe I'm not trying to predict like the career outcome of a baseball player. I'm trying to predict like people who play the game in a similar way. That might be a clustering type approach. And again, it's unsupervised. So here's a visual example. So here you have raw data on the left. A human might say, oh, maybe there's 3 or 4 clusters. An algorithm might actually be able to tell you, well, actually there's like 7 clusters, some of which are nested within other clusters. And then just to drive this home, machine learning can be broken out into supervised learning and unsupervised learning. There's also reinforcement learning that's a little bit different. And then supervised learning can be classification and regression. And again, this is a bit oversimplified, whereas unsupervised learning is typically clustering or something similar. So again, this is very high level. I'm leaving out a lot of the key detail here, but some of my colleagues will build upon it a bit. I'm going to pass it off to Justin Wynn, and he's going to talk about what's possible.
Okay, thanks, Levi. Thank you for that great overview. So one of the most exciting things about data science is that you can apply it to everything. And when I say that, I definitely mean it. Before I jump into too much detail, though, first let's take a quick poll.
All right, you should be able to see the poll on your screen right now. So if you guys could just take a few seconds to vote. The question is, how can data science best help you in your day-to-day life? All right, and while y'all are answering, I did want to just make a reminder that if you have any questions, please type them into the Q&A box at the bottom of your screen. We are monitoring that and we'll answer them at the end of the webinar. All right, just a few more seconds. All right, it looks like the majority of the group wants to predict the stock market. All right.
Anyway, so with data science, it's just a really, really exciting field to be in because you can do so many things with it. And some of those questions or some of those answers that you saw in that poll are real things that you can do. I've used data science to make me a better fisherman. I have an algorithm that can predict the best times to go fishing based off of the weather and the marine conditions. I have a program that monitors my emails and alerts me if it senses urgency and extreme sentiments. I also wrote simulations to predict how many guests were going to attend my wedding. So in short, there are many, many exciting things that you can do with data science. For the sake of time, I'm not going to cover all of them. I'm just going to cover 2 very popular, very simple, and very powerful use cases. So the first is automation. Some of you may have heard of robot process automation or RPA. Basically, all this is just taking a business process and automating it. One of the advantages with doing projects like these, one, they are low risk. Typically, with projects like these, you have a very defined business process with known requirements, and you're really trying to stay away from going in and making any crazy changes to any existing systems and processes. And the second thing is that the value is very transparent. The cost and the time savings is very measurable, and this makes it a pretty attractive option. So one example of automation is document processing. This is something that everyone has to do, and I know everyone loves it, right? Paperwork is everyone's favorite thing to do. We all love to be this admin in the middle. But yeah, so with document processing, there's lots of different flavors. Maybe you are processing invoices. Maybe you are collecting reports that need to be aggregated. One common scenario is with accounting and financial reporting. Anyway, there are many different examples. Let's walk through one example. In this case, we're going to deal with working with construction project documentation. So with a construction project, you basically have documentation being generated from everywhere, whether it's from the construction contractor, engineering and inspection teams, even the instrumentation is generating documentation. And in this past project, all of that documentation was being sent primarily through email to some compliance specialists who had to review and approve this documentation and then file it away in a couple different repositories. So this is, if you're one of these admins, this is a very tedious and manual process. Each person has to open, download, save hundreds of attachments every day, convert and standardize a document, review it, and perform many other document processing tasks. Now, things can get a bit tricky when you try to automate intelligent logic in this process because you can't necessarily just hard code everything. When you're building guidelines, you need to build a bit of a balance. You want the system to be flexible enough to accommodate different rules without crashing, but not too flexible to the point where you just allow garbage and chaos to pass through. So with data science, you can apply some advanced applications like natural language processing and computational linguistics that allow for this. These intelligent systems can decipher and understand text through things like inverse text normalization and fuzzy matching algorithms. This probably sounds like a bunch of nerdy buzzwords, and they probably are, but they lead to real results. Some big things I want to point out with this project, one is the cost savings. We save them thousands of dollars per day. On top of that, we freed up 80% of their human capital to go pursue other tasks. We also significantly boosted accuracy and speed. For example, we automated significant portions of the document review so that the approval and rejection process took hours instead of days to do. One of the benefits of doing that is now you're getting approved data much faster, much closer to real time, which is going to result in significantly better business intelligence reporting. So automation was the first big case. The second one we'll cover is this idea of discovering insights. One of the common things I hear is, Justin, I've got experts in-house who have decades and decades of experience. What is data science going to tell me that I don't already know? And to that, I say, yeah, you're right. No one understands your business better than you do, but everybody has blind spots. And that's where data science can come and present a different angle, or maybe a different, unbiased view, or maybe a more holistic view. There are two simple situations below. So the first graph on the left, this appears to be just noise. I mean, there isn't really any obvious meaning in these data points, and it's pretty difficult to decipher. But with data science, we can actually slice and dice this data, as well as do several transformations that are, in fact, able to find trends. The second graph here on the right, so a very common approach that I've found with clients in the past is that they like to lean pretty heavily on averages or moving averages or sums. And the problem with that approach is that it underfits your data and you lose a lot of valuable information. In many cases, like retail or hospitality or travel, there may be a very strong temporal component to your business. Maybe there's things like seasonal trends or weekly or daily or even hourly trends. And so with data science, you can create much better forecasts and have better planning by just simply using modeling techniques with greater precision. So another powerful tool for finding insights is latent modeling. Latent modeling is an extremely powerful technique. It's got a huge range of applications from advanced customer segmentation to image reconstruction. There's a lot of math that we're not going to get into. It's just easiest to explain with a visual and an example. So let's say on this slide right here, we have a very, very large population. There's a very large number of individuals, and each individual has a large set of attributes. This could be something like maybe you're analyzing crime in a population, or maybe you're trying to solve a public health problem and you're trying to find, high-risk assets. So the challenge with this is a huge amount of data that require way too many subject matter experts to analyze. Visually, it looks something like this, where there are many, many data points spread out over a very, very sparse multidimensional space. With data science, we can actually start cutting and reducing this down. And we can do this in many different ways. We can find commonalities based on an attribute, or maybe a group of attributes, or maybe by groups of individuals. Anyway, this is a very powerful tool because it gives you so many different angles very quickly. So anyway, automation and insights, those are just two of the many powerful applications of data science. Sorry, I think there's a bit of a delay. So these automation insights are just two of the many powerful applications of data science. Thanks everyone for calling in and giving your time and attention. If you have any interest or questions on data science, please reach out to me or any of the great any of the great consultants here at SenseCorp. And with that, I'll kick it over to Dan.
Thanks, Justin. Sorry, I'm still a little bit dizzy from staring at the latent model diagram, but I'm going to try to recover. So I think we're going to give you a couple case studies. The first one that I'll talk about is not concerned so much with particular models, but with a more overarching methodological question that data scientists face. And that's, can data science models travel? So in this case, we're predicting churn in cable TV and then in education. So can data science models travel? In other words, are models transportable across industries? Or is each industry or each company or each particular question so unique that it requires its own distinct model development? So the starting point for this question is in cable TV, and that's my home base, as Kelly mentioned earlier. So I've spent more than a decade diving through millions of cases over several years, developing models of cable TV churn in particular. These models have matured through several iterations across multiple clients. We've been able to triangulate with qualitative analysis, like listening to customer phone calls and looking at surveys. And we've developed some pretty good predictive models of cable TV churn. So we have around 16 drivers, and we think this gives a pretty good prediction of whether a cable customer is going to disconnect or not. So that takes us to the question, can we use cable churn models to explain student churn? We had a couple clients in the education space. One was a vocational school, one was a public community college, and they were both grappling with questions about their own students dropping out, whether the student dropout rates were increasing or more volatile than expected. They were trying to explain student churn. And when we came on the scene, we thought, well, can we use the models we had already built for cable churn in order to explain student dropout rates? And we saw a couple benefits of this. One benefit is that we thought that broad concepts like churn and some of the drivers could very well operate across many industries. Another benefit is that schools tend to be small and cable companies are huge. And so a small N industry like a school can potentially draft off of large N analysis and overcome some sample problems that may have otherwise existed. Along with these benefits, though, we saw some risks. And for me in particular, in a past life, I was in a graduate program in comparative politics. And the risks that I saw stemmed from risks that were noted in the comparative politics literature. And so it's going to be a little bit wonky here, but hopefully I'll be able to explain it properly. So one of the risks is the danger of conceptual stretching. In other words, a concept that means one thing one place doesn't necessarily mean that same thing somewhere else. Similarly, there's a risk of extrapolation fallacy. In other words, just because A causes B in one instance doesn't mean A will always cause B everywhere. And then finally, some industries may really be unique. Maybe education is so unique that we really did need to reinvent the wheel and we couldn't leverage anything from cable. So we went into this analysis mindful of the risks, so we decided to plow through. And here's the methodology we used. We first sought out these comparable models. So we looked at cable TV and we, as a starting point, started with those 16 drivers that we had identified. We then climbed this ladder of abstraction, and this is kind of a cool metaphor here, but basically what we're doing is we're taking discrete drivers or discrete independent variables, and we're abstracting them up into concepts. And then we take those concepts and operationalize them back down to discrete drivers for the target, for student dropout rates. And the next slide is going to show how we do that. And then once we end up, sorry, go back one more. Once we end up with that target analysis, we then assess and mitigate the risk. So the result in number 3 is really the starting point to then dive into discussions with subject matter experts. So at SenseCorp, we didn't have any data scientists in the education field, which is why I came in, but we did have a lot of subject matter experts. We also had the opportunity to have interviews with numerous subject matter experts in the clients who gave us anecdotes and their perspective on what could be driving student churn, and also pointed us to academic literature. And then we could also use statistical methods in order to ensure that when we're borrowing a model from another industry, we're not making a mistake. So we started with these 16 cable disconnect drivers, and we climbed the ladder of abstraction. So we ended up with 16 conceptual churn drivers. And some of these are kind of the same. So some of the cable drivers were already kind of abstract, but you can see that something like reception quality becomes an overall product quality. Something like campaign roll-off, which in the world of cable means that, let's say you signed a 1-year agreement and it's about to expire, and you have to decide whether you want to re-up or not for another year. That becomes a more conceptual decision point. So an inflection point when a customer, maybe they kind of, get their bill every month for a year, or maybe even pay electronically. They don't really notice it, and they get a letter in the mail saying their campaign's about to expire. That becomes a decision or inflection point. That's the concept behind it. Income for a cable customer, maybe an overall economic trend is the concept behind it. So now we're at this conceptual level at the top of the ladder, and then we climb back down. So now we get a potential list of student dropout drivers, and we have 16 lists, and you can quibble with kind of how we move from one to another, but we thought that, or at least I thought, from my perspective of having very little knowledge of education coming in, I had a pretty good start to some potential drivers of student dropout rates. The examples that I gave, reception quality became product quality, and that dropped back down the ladder into teaching quality. The campaign roll-off became a decision point, and a main decision point for a student is at the end of a semester. Do they renew and re-enroll for the next semester? So we're definitely not done at this point, but we have a good start. The next step is to go through these risks and figure out how to enhance or tweak or correct the model to account for these risks. So the first risk is this conceptual stretching. And there's 2 things we found here where concepts didn't seem to be traveling well from cable to education. The first was an interaction. In the cable world, if you have an interaction with somebody from your cable provider, that's usually not a good thing. It may have a good outcome. You may have your question answered or your equipment may be repaired, but the fact that you had to talk to them at all is probably not good. In the student world, what we found from talking to subject matter experts is that interaction is really the glue that holds students in the school. Interacting with fellow classmates, with teachers, with tutors, the more interactions they had, the greater the likelihood they would be retained and finish their degree. And so interactions really worked in opposite directions. Similarly, economic indicators for a cable company, when the economy does better and incomes go up, that's good news. People have more disposable income, they're less likely to cut the cord. Interestingly, what we found from talking to subject matter experts in education, especially in the vocational school, is when the economy is good and jobs are plentiful, that actually puts pressure on churn. Churn goes up because the opportunity cost of staying in school increases. and there's less motivation for a student to finish and more motivation for them to drop out and take a high-paying job. And so once again, we saw similar concepts about like in the economy and interaction that actually might work in opposite directions. So the second risk here is related, and that's the fallacy of extrapolation. And we had to be careful not to assume that just because something drove a behavior on the cable side, it also drove behavior on the education side. So the first is that the act of churning, of disconnecting, is different for a cable customer than for a student. For a cable customer, it's kind of a temporary thing. A lot of people do this thing where you're with one provider, then you disconnect, take a promotion, another one. A few months later, you qualify for the better promotion at the first one, and you kind of go back and forth. Students are much less likely to do that. There's greater impediments to re-entry once they drop out. And then second, in terms of price increases, that can be a really important driver of cable churn. When prices go up, cable customers can be very price elastic. For a student who's getting grants that cover the full cost of the tuition, especially at community college or at vocational schools, price may not really matter because they may not bear the brunt of it. And so students may have a much lower elasticity of demand. So finally, the third risk that the industry is unique, and this is where we really had to have enough discussions with our subject matter experts at SenseCorp and with the client to really understand other things that we didn't include in the model to begin with. So one is that prior credentials matter. So for a cable customer, and speaking from personal experience, when I enroll or sign up for a cable company, the fact that I've maybe seen every episode of Golden Girls twice doesn't really matter for my likelihood to churn. It may have given me a lot of life lessons, but it doesn't necessarily make me more or less likely to disconnect. For a student, prior credentials and achievements really do matter. So if you, for instance, have your GED versus a high school diploma, that can be a really important data point in predicting churn. Another important part about student churn is that student churn is right-censored, meaning that students graduate. So let's say you're in a 2-year program. If you're a year and a half in, you have a lot of motivation to get through the last few months. For a cable customer, that doesn't exist. So it needed to be built into the model of student churn, and when it didn't for cable TV customers. And then the final one, which the first day we were told this, and it seems obvious in retrospect, but it really wasn't obvious to me, is really the seminal importance of transportation. Having access to a car, having access to a bus line, or living close to a school is hugely important for student churn, especially at community colleges and vocational schools. Whereas for cable TV, it doesn't even come into the picture. So the upshot is that we were really able to start at a really good place by leveraging cable TV churn driver models when we went into this educational world, but that couldn't be the ending point. We had to then combine that starting point with a lot of subject matter expertise in order to build a robust model that didn't just work for cable customers, but really worked to explain student churn as well. So I think this gets at the larger questions of data science. You know, are data scientists just people who go from place to place deploying the same models, or do they really need to work together with people who understand the material and understand the industry and the company? I think to Levi's description at the beginning, it's really the latter. It takes the combination of statistical knowledge and computer knowledge, but also of subject matter expertise in order to really develop the right models. With that, I'm going to turn it over to Levi. Thank you.
All right, thank you, Dan. So similar to what Dan just did, I'm going to kind of do a compare and contrast between two different use cases, this time in the field of predictive maintenance. And we're going to basically be talking about a large oil and gas company, as well as a large fleet management company, and the kind of the nuances of the different modeling situations. So this question of how do we predict maintenance outcomes is increasingly crucial for companies, especially those who operate with very expensive assets that are oftentimes spread across the globe. Our personal approach is we leverage a lot of what we know about population health, and this lets us dip into literature not only from more traditional fields such as industrial or mechanical engineering, but also into some things that can be learned from the life sciences even. And anytime you're talking about maintenance behavior, you're really dealing with a population that has a healthy component, which is hopefully the larger part of your population, as well as a sick population that is intermittent. So, assets within this population might come in and out of being sick depending on how they've been serviced. So when we try to draw inferences about this population, we need to make sure that we understand both components. The issue there is there's a bit of a reporting bias for the, quote, sick population, and that's just kind of a part of business. You're much more likely to take really good records on things that are broken than really good records on things that are up and running and working perfectly. So we frequently spend a lot of time searching for missing and or low fidelity data. So maybe they do have some, current status information on their healthy assets, and maybe we need to enrich it in certain ways. And actually, this is becoming a little bit easier with this new generation of streaming IoT devices, which can give you, up to the minute telematic style data. And another thing we do frequently here is we work across multiple granularities for best outcomes. So I'll give you a concrete example. You might have this really specific part for this really specific machine, of which there's like 6 in the world, and one of which is broken. Pretty hard to draw concrete statistical insights from when the N or when the total population is that small. However, maybe you can bring up a level of granularity to maybe it's the family of parts, and in the family, there's 300 similar parts, and maybe we can make better insights at that grain and bring them down to the lower grain with a little bit of tuning. So going back to those 2 clients, so one is an oil and gas services company, and they were really trying to predict the best way to service specific maintenance events. So that's more of an outcome-oriented approach. The second client is a large fleet management company, and they were trying to operationalize statistical insights to understand basically the life cycle, or how to manage this product across time and the total cost of ownership associated with any decisions they might make in terms of servicing it. So is it even worth putting that new engine in the vehicle, or might we want to do something else? So these are a little bit different in some kind of subtle ways, but they do have some similarities. So they're similar in that these are expensive assets with multiple type of maintenance events. So you want to be really careful about how you're servicing them. It's not replacing a tire on a bicycle. It's replacing like some heavy duty expensive stuff. And there's a lot of complexity there. There's also a lot of difficulties in predicting unscheduled maintenance events. So these machines and across lots of industries operate in very different environments. So you might have one machine that's subject to pressures that another machine isn't at all. So it can be kind of hard and nuanced to understand the unscheduled types of maintenance behavior. And then lastly, there's a disjointed connection between the service and outcome data. And this really comes down to kind of a data engineering or infrastructure exercise. So oftentimes you might have 2 different systems, one for capturing records from maintenance, and another one for capturing maybe like resale activity or warranty activity. They don't necessarily talk to each other in a unique way. And if they're disjointed in that way, it can be really hard to draw insights, because first you have to create a kind of logic to bring them together. They're different though in some pretty specific ways. So though they both share that idea of disjointed connection between the service and the outcomes, that's disjointed for different reasons. So sometimes you might have, it's a software problem. So these 2 pieces of software don't really talk to each other, and you have to make them talk. Sometimes maybe all the data is housed within, like, say, a central ERP system, but it's actually the business process that's in need of improvement. So we want to change how we're inputting data. We want to change how we're handling the metadata, that kind of stuff. And then also there are divergent goals with each client. So one client is really trying to understand a distribution of outcomes. So in like a temporal way, what's my likelihood at this time period versus this time period? And the other is really trying to understand a result. So given that this maintenance event happened, what are the likely next steps that are going to be necessary to take? And then how do I choose the best one, essentially? So in summary, They're similar, though they have some context-specific differences, and that's something we find across all clients. So, take you through a quick little step-by-step. So, first, we have to wrangle the data into a usable form, and this is really, again, creating logic to bring together disjointed records. So, frequently we're working either with internal subject matter experts or at the client. This might be a little bit easier if this is an internal effort on the whole, where everyone has this deep context. But you really need the context behind why things are not talking to one another. And here we leverage a lot of our data engineering skills. We have a lot of great people who do a lot of data management or ETL development, and they can really help with this process. We also frequently perform data quality work here. And what's really cool about data quality work is frequently ancillary insights fall out. So what might look like a data, maybe some outliers and you think it's a data quality problem, well, maybe those outliers are real and something is actually broken elsewhere that you need to go fix. So once we've kind of wrangled the data, we then model it. And here we're using statistical methods to build, select, and test models. So we always try to determine our experimental design and kind of like Dan talked about, the methodologies we're going to use up front, and then also what constitutes success. So it's a slippery slope. You can start kind of changing requirements to better fit your model if you don't set this up front. We then spend time modeling distributions and exploring features. So this is like exploratory data analysis, and this is trying to really understand, the underlying patterns within our data and kind of what's going on. And this is time well spent, even though sometimes it can kind of feel a bit like you're wandering random paths, because any time you spend here will help you on the back end of making sure you're producing a model with good assumptions built in. And then lastly, meat and potatoes part, we train, validate, and test our final models. So making sure we're doing statistically rigorous work, and we are always checking for statistical pitfalls. So it's really easy to overfit a model in pursuit of a great result, or it's easy to operate on faulty assumptions if you're trying to do something that's difficult. So all of our data scientists try to operate with an air of skepticism in their work. And then lastly, we operationalize the model. So we try to make it easy for business users to access insights. So sometimes that's just creating a scripted job that's going to print in like new data out of our models to a table, and that we can build a decision support tool around that with some of our digital assets. We also sometimes will provide self-service visualizations. So like we've built models that integrate with Tableau and MicroStrategy, so it's easy for business users to access the insights. And then also you always want to make sure that you're producing a model that self-corrects with changes to the data and business. So we produce this great model, it's kicking out these insights, it changes how we do business. We want to make sure that the model then adapts to these changes. So some final thoughts, I'm gonna hit these at a high level. So how to improve the quality of insights, and it ultimately comes down to garbage in, garbage out. So if the quality of your data infrastructure and management isn't high, your ultimate model won't be very good. And also if you're sourcing the wrong data, so like, let's say in the modeling process, we realize that we have this one piece of information, everything will be better. Sometimes we want to change how we're sourcing our data to go get that information from our customers, or in this case, the assets. Maybe put a new sensor on your asset in the field. And then workforce upskilling. So maybe we're taking business analysts who have deep subject matter expertise, and we're upskilling them with Python and statistical skills to become data scientists. And then how do you best act upon insights? So these are just a couple of methods, but it really comes down to like, can you take these predictive and sometimes descriptive insights and make them into more prescriptive? So maybe you create a simulation of your business and you alter the parameters. So I say, hey, if I actually wait till 100,000 operating hours instead of 80,000, how does it change my business? And you can build a model to simulate that. And there's a couple other approaches. I won't go into them too deep in the interest of time, but some of the stuff Justin had talked about with regards to automation, really awesome. So if you can automate away time spent by your FTEs on lower value added tasks, they then have more time to put towards the higher value added tasks that maybe computers aren't quite as good at yet. So with that, I think I'm gonna move into the Q&A session. So just in summary, today we've talked about kind of an introduction to key terms. We've gone through what's possible with data science, and then talked through a few different compare and contrast cases to kind of show you how does this work in the real world. So I think Kelly has a few questions.
I do. All right. Thank you, everyone. We do have a few questions that came in. I'm going to go ahead and ask those now. And if you have any other questions, please feel free to keep typing them in. I know we just have a few minutes left, but I think we'll be able to get through a few of these. So the first question is, how does natural language processing fit in with AI? Justin, I think you might be able to take that one.
Yeah, I can take this one. So natural language processing is a subfield within the AI umbrella. It seems kind of strange to think like, how does math and text kind of mix? But it actually mixes very, very well. And there's more and more natural language processing applications coming to the market. Like, for example, if you've used Siri, if you've used Alexa, chatbot technology, Google Translate with language translation, those all use natural language processing techniques. And the approach with those is it's a lot of analysis with grammar and syntax, entity recognition, topic recognition, and basically a field where we're trying to teach computers to have a better understanding over natural languages, not just English, but all languages of the world.
Okay, thank you. Another question here is, what is the current language used by data scientists to query data residing in data lakes?
Yeah, so I think I'll take this question. So up front, I'm going to explain a little bit what a data lake is in case anyone isn't familiar. This is at a very high level. We have architects here who are much more familiar with the nitty gritty here. But if you think of a normal like a data warehouse or a data store as you've got your data coming in and you're processing the data to a degree before putting it into storage to be accessed later by business users. A data lake is a little bit more free form. So we ingest the data in its like natural form, or it's organic, which is a funny way to describe data form. We just dump it in storage, and then we process it on the way out. And a key advantage of that is you can store structured and unstructured data alongside each other pretty easily, as long as you know how to process them on the way out, so on kick out. So the question specifically asks, what is the current language? I don't know if I can offer like a super, this is the answer in the way that I can with some other languages, but there are a few languages out there that play nice with data lakes. The only one I really used, this is more on a trial basis, was USQL, which is for playing with the Microsoft stack. And what USQL is it's a flavor of SQL that combines just normal SQL style declarative stuff with C# imperative stuff. And what that lets you do is I can both process the data, because the data is not processed in my data lake on outbound. So I process it with some of the C# stuff, and then I can use that pretty standard SQL style declarative syntax to query it in the same way I might query something more classically structured. So there's a few different languages. They all, I think, kind of come down to like versions of SQL plus some imperative processing language, because you need that with data lakes. That's it at a high level. I can answer some follow-up questions if necessary, or you can follow up with us directly. We'll share some contact information.
All right, we are almost at the top of the hour, so we're going to go ahead and cut the Q&A session now. I wanted to thank our panelists, Justin, Dan, and Levi. Great job. Thank you for all of our attendees. Keep in mind, I will be sending out a follow-up email following the webinar that will have the recording, and I'm also going to be sending out a survey that is going to ask for, basically answer where you are in your data analytics journey. So look for that in your email, and thanks again. Hope everyone has a great day.